Hello, ladies and gentlemen. This is Ms. Bashauer. We are continuing along in our unit on exponents here. This is the third section of Chapter 11, and we're going to talk about some really interesting applications for exponential functions in the real world. We're going to talk about exponential growth, and we have a formula for that. We're going to talk about one example that is really quite useful. It has to do with money and how you collect interest, and that's compound interest. That has its own formula. We're going to do some real-world calculations that involve exponential decay. Exponential growth and exponential decay are very similar, but work in somewhat of an opposite fashion. One, when things grow, well, we have a pattern that grows, and obviously one where we have a pattern that decreases as it goes on. We have a formula for that. It's very similar to the formula for exponential growth. And then we have a really interesting example of when we would use exponential decay in the real world, and those are called half-lives, or the half-life. Maybe you've heard of that in science. If you haven't yet, you probably will next year in 8th grade. Then you know that is a topic that you will see a lot in science class. So let's begin. We start with exponential growth. Okay, here's our formula for exponential growth. And this box here tells you what all of those variables stand for, x and a and r and t. Okay, exponential growth occurs when a quantity increases by the same rate r in each time period. Okay, what's different about this formula from the other ones we've had is we're generally talking about rate as a percent. Okay, what percent is it growing up each year, each week, each day? Okay, this will be a little clearer when we do an example, so let's do an example. You may want to grab a calculator. I'm going to do that right now myself. You may want to grab a calculator because we are going to have some definite use for it here, some big numbers that we'll just punch in. So most of our work today is just basically going to be evaluating a function. What does that mean? We start with a formula, we plug in numbers, and we follow PEMDAS to figure out a missing variable. Okay, clearly there are 4 variables going on here. We'll generally have 3 of them and trying to find the 4th. The one thing that I want to note is r, your rate, is expressed as a decimal. Okay, just be careful of that. Here you can see a percentage that's going to go on in our problem. That's going to be our rate. And we're not going to put in 8. We're going to put in that percent written as a decimal. Okay, if you don't remember how to do that, I'll give you this example of 8% would be 0.08, just 2 decimal places over. Okay, so a sculpture, let's do the first one together. I'm going to have you guys do the second one. A sculpture is increasing in value at a rate of 8% per year. Maybe it's increasing in value because it's becoming an antique. It's becoming more interesting as something to buy. And its value in 2000 was $1,200. Write an exponential growth function to model this situation. Okay, so that's going to be step 1. Just kind of create a function, an equation that would model this situation of the sculpture, and then find the sculpture's value in 2006. Okay, so let's start by writing our formula, or plugging our information into our formula. We are going to have y is something we don't know yet. A is the original amount. Okay, so this is worth $1,200. The 1 is always there. Plus 0.08 is our rate, and then our t is, I guess, what our second variable will be for now as we do step 1, and then the sculpture's value in 2006. T represents time. We're not going to plug in 2006 here. We're going to plug in how much time do we allow this exponential function to continue to model this increasing value of our sculpture. How much time are we going to be talking about here? Well, from 2000 to 2006. So our time, you probably guessed it, should be 6 years. So y equals, I'm sorry, and this isn't actually done yet because we can do this addition, 1.08 t. Okay, so this is basically your final answer for step 1, which is just to write a function. And then step 2, we're now going to plug in the value in 2006, and that's going to be after we let our sculpture sit in the attic maybe for 6 years. We want to see how much it's going to go up. Again, not super complicated. Grab a calculator, but just make sure to follow PEMDAS. I'm going to do my exponent first, 1.08 to the 6th power. If you want to check my calculations, that would be great. Punch this in with me as I go. Now, my calculator is a very large number. I'm going to round to, I'll keep 3 numbers after the decimal point. How does that sound? 1.587. And then we multiply that number by 2,000, and we get y is equal to $1,904. Whenever we're talking about dollars and cents, always round to the nearest hundredth, because that's as far as we can cut up a dollar is into pennies. And our final answer there should be $1,904.25. Yes, that is correct. And I guess that makes sense. You get a little bit more value of your sculpture every year, about 8%. If it starts out at 1,200 and you leave it sit for 6 years, that's pretty nice of an increase there. You're gaining about $700 just by hanging on to that item. Okay, so I'd like you guys to do this example too, or number 2. It's talking about the original value of a painting is $1,400, and the value increases by 9% each year. Okay, so we're going to get an even higher percentage. Okay, maybe we'll get 700, maybe not. It depends on how much we start with, and it also depends on how many years we let it sit for. 25 years is a pretty high amount, so hopefully that will give us a nice increase in our investment. So go ahead and hit pause, try this problem, and come back. Right? I assume you're back. Step 1 is to simply figure out what your equation would be. A, and hopefully you took a second up here to write down the formula. A was our original amount. So our original amount in this case is $1,400. And R was our 9%. These two amounts here in these parentheses can get added together. So our final function, equation, is here. Hopefully you got that for step 1. And then step 2, you can plug in 25 years. And this is pretty remarkable, ladies and gentlemen. You can go from $1,400 to $12,000 simply by letting your painting sit for 25 years. You know, obviously assuming it's going to increase 9% per year, which, you know, maybe is realistic in the real world and maybe not, but it's an interesting application of exponential functions. Okay, so like I said, hopefully you have that formula written down. This is exponential growth. Okay, we're going to keep moving. Next, we have compound interest. Compound interest is just an example of exponential growth. Compound interest is what banks use to calculate how much money you have in your bank account, assuming that they give you a certain interest on your investment. Okay, back in pre-algebra in 6th grade, we did simple interest. If you remember, simple interest was interest equals principal times rate times time. You just multiply those 3 things together. That's a really great stepping stone for understanding interest, but it's not realistic. Okay, we don't use that in the real world. We use compound interest. Okay, compound interest is here, and there's a lot more things going on because you shouldn't only calculate interest after your 5 or 6 or 7 years. You should stop and calculate interest along the way and then add that back into your principal. So that's kind of the idea of compound interest. Interest is paid on both the principal and the previous interest you earned in the years before. Okay, so I'm going to start by writing down that formula here. P 1 plus R over N and N times T. Okay, the principal in this particular example, number 1, $1,000 invested at 3%, compounded quarterly, and then set for 5 years. Okay, what compounded means is that how often are they going to stop, calculate the interest that you made, and add it back to your principal. Okay, compounded quarterly means every quarter, so that means 4 times a year. Okay, 4 times a year, every 3 months, they're going to stop, calculate how much interest you got, and then add it back to your principal. Okay, so what we're going to do here is the same as what we did before. It's just kind of pop in the numbers to our formula. evaluate using PEMDAS, and figure out what piece we're missing. If we are figuring out $1,000, that's going to be our principal, so that's your 1,000 here. We have 1 plus R over N. R is the rate, so that's going to be, in this case, 3%, 0.03, over N. N is the number of times it is compounded per year. Ours is compounded quarterly. Quarterly means every, you get to divide by 4. So 4 times. So that goes there. And then parentheses, and our exponent is n times t. N is that 4 again. And then t represents the time in years. And in this case, it will be 5 years. Okay? And we're just kind of plugging and chugging here, guys. 1,000 times, and grab that calculator, 3/100 divided by 4 is a fairly small decimal, plus 1.0075, and then up here we'll have 20. Okay, from there, I will move over here. From there, I can just simply plug that into my calculator again to the 20th times by 1,000. So, we have a final answer. I guess it's A in this case. $1,161.18. Okay? What's nice here is that you're gaining money by just letting your money sit in the bank. Okay, 3% is a fairly small percentage, so you're going to really only earn about $161 in extra interest money in 5 years. Okay? But hey, it's free money, so you can't turn it down. I want you guys to try number 2. Hopefully you took a second to write down that formula up there at the top. And go ahead and hit pause, give that one a try, and we'll come back. All right, I assume that you're back from trying number 2. Your answer here, if I can walk you through the steps, we'll start with the formula. We'll plug in the numbers that we need to plug in. Our principal is what we start with. That's $18,000. The 1 is always there. The R is your rate. Turn it into a decimal. And your N is compounded, how many times per year? Compounded annually. Annually just means once. Just 1 time per year. If you were confused on that, go ahead and now try it, now that you know that your N is equal to 1. And then T is for 6 years. Okay, so this was the formula that you would have. You can plug in 6, and you would get about $23,000 total. So you made an extra $5,440 in interest, which is great. Okay, those are the 2 topics that have to do with exponential growth. Okay, so clearly we're ending with a number here that's larger than the one we started with. Something is growing at a certain rate. Okay, exponential decay is just the opposite of that. And if you look back at our formula here, this, take a mental picture of that right now. Sorry, Mr. Beata is making a guest appearance on our video today in algebra. I'm just going to keep going and talking over him. This is our function for exponential growth. And if you can take a little mental snapshot of that, here is our function or formula for exponential decay. Clearly, the only thing that's really different is the subtraction sign. Now you're taking away as before you were adding. Let's try an example together, and then I'll let you guys try one on your own. Okay? Y is equal to A minus R to the T power. A fish population in a local stream is decreasing at a rate of 3% per year. Oh, that's sad. Okay, the original population was 48,000 fish. That's a lot of fish. And so that's A. The 1 minus is always there. The rate is 3%. So now we are writing as a decimal, 3 there. Your T is 7 years. Okay, if your first step is to just write the function, we're going to simply put together a few things that can go together, which would be this here. 9,700 to the 7. Oh, gosh, I'm sorry. I guess if we're doing our function, we're supposed to leave this as t for now. We'll leave that as t for now. And then we can use that function that we wrote there for what's going to happen in 7 years. So now we can plug in our 7 years, one more 0, to the t for time, and punch that in your calculator, and it will tell us how many fish we will have left in 7 years. I'm running out of space, so I'm just going to write it across here. 38,783 0.2 fish, I suppose. That may not seem like a lot, but that actually, I mean, to me, that's a lot of fish. That's 10,000 that you just lost, going at 3%, only 3%, but over 7 years. They're going to keep losing and losing and losing because there's going to be less fish to make fish babies. Okay? So you can see how this would be important in the sciences. You know, people who want to study animal populations and a certain animal's impact that they might have on their surroundings and how other predators coming in might change. You know, so it's a really interesting topic, I think, that connects to science quite well. I'm going to have you guys try number 2. Hopefully you took a second to write down that formula there before you start the problem here. We're mostly just plugging in our formulas and following PEMDAS. A population of a town is decreasing at a rate of 1% per year. In 2000, there were 1,300 people. Write an exponential decay function to model this situation and find the population in 2008. Okay? So hit pause, give it a try. All right, I assume that you're back. And your answer here, hopefully you have, this is your function here. And our town is down to 1,200 people. Okay? Which, you know, if you're only starting with 1,300 and you lose 100, I guess that's a pretty significant amount. So that is just a basic introduction to population, not population, exponential decay, kind of the opposite of exponential growth. In both cases, something is changing exponentially. In this case, we are losing people or losing fish, depending on your situation. Okay, we're going to do one more example of just like how we did compound interest as an example of exponential growth. We're going to talk about half-life. And half-life is a very interesting topic also that has to do with science. The formula is here. And it is talking about basically a certain substances that will decay. Generally, we're talking about decaying compounds here over a certain amount of time. So a half-life, the half-life of a substance, is the time it takes for one half of the substance to decay into another substance. I don't know what it's turning into, but it's decaying. Okay, so talking about fluorine. Fluorine is an element on the periodic table, and it has a half-life of 11 seconds. So every 11 seconds, it's going to change into something else. Find the amount of fluorine left from a 40-gram sample after 44 seconds. So the first thing we need to do is find T. And if you look up T up here, T represents the number of half-lives in a given period. Okay, how many times is that amount that we started with going to be cut in half? And if I have 44 seconds and fluorine has a half-life of 11 seconds, I can just say 44 seconds divided by 11 seconds is 4 half-lives. Okay, that thing is going to be cut in half 4 times. Once I know that, I can plug that into my formula. A is equal to capital P, 0.05. That 0.05 comes from the fact that you're cutting something in half. And A represents the final amount. P represents the original amount. So I'm going to plug in my original amount is 40 grams. And T is the number of half-lives. And mine was 4. Do some PEMDAS here. 1/2 to the 4th power multiplied by 40 will give me 2.5. You can see how quickly it will turn into something else if you're not careful. Now, I need a label on that because this is a real-life situation, so it's got to be 2.5 grams. Okay. One last problem. I want you guys to try this one. It still has to do with fluorine. Okay, so you're going back to fluorine 20. Has a half-life of 11 seconds. Find the amount of fluorine left from a 40-gram sample after 2 minutes. Now be careful. 2 minutes is also the same as 120 seconds. That's a big hint as to how you might figure out your T value. Okay, that's your first step. Up here, we first found T, and then we use our formula. So give this one a try. Go ahead and hit pause. Now, please. All right, let's talk about this last example. Fluorine. Oops, I'm sorry. That is supposed to disappear. Oop, bang. We'll just slide it down here. Okay. Step 1 is to find T. And if I have 120 seconds and I'm dividing them into 11-second intervals, I'm going to have about 8 half-lives. I don't think that is an exact number. 120 divided by 11. I didn't get 8 at all. Divide the time. I'm punching something very different into my calculator, maybe. Divided by. Let's talk about this one tomorrow in class because I'm not getting 8. That could be a mistake they did in the textbook. We'll have to discuss this one in class tomorrow. I think that's an interesting point. Maybe we have found a mistake in our textbook. Let's pretend it's 8. If it happens to be 8, you're going to put 8 here. P is your original amount of 40. And then you're going to calculate that, oh my gosh, there's only 2 hundredths left. And now if we have 11 half-lives, which is what it should be, we're obviously going to have much left. Much less left after 11 turns. Okay? So we'll talk about that one tomorrow. Hopefully you guys feel good about these 4 different formulas that we used. Okay, we talked about exponential growth and exponential decay. And then we simply did one example from the real world for each one of those. For exponential growth, we talked about compound interest. And for exponential decay, we talked about half-life. Okay, guys, bring any questions that you might have to class tomorrow. We'll talk about that weird answer that we just got on that last problem together. And have yourselves a great evening. Let me know if you have any questions. Bye-bye.